Good morning, students. Today we are going to discuss about the RPM meter. So the main intention of the RPM meter is to calculate the speed of a particular wheel or speed of a motor, anything. So which element speed you would like to calculate, you are going to make use of the RPM meter in that element, so that it is going to be senses the speed of that particular element. Okay, so that is the main intention of the RPM meter. Now, how the RPM meter is going to be work is a question. So, if you want to know that one, what we do is before going to the complete block diagram, we'll go for the basic the overview of the blocks available in the RPM meter. So, in the RPM meter, we are using the variable reluctance type sensor as a speedometer, which calculates the speed. There is a rotation of element to which you would like to calculate the speed. So the output of that particular sensor is connected as an input to the signal conditioning block. So over here it is a signal conditioning block. The signal conditioning block is intention is to bring the output of the transducer, output of the transducer, which is a low intensity signal, into a certain high intensity, means to amplify the information. We are having the signal conditioning block. It is just like acting as a amplifier, instrumentation amplifier. So we know that it is a instrumentation amplifier, which you have seen in the what E&I classes, during the E&I classes. Okay, so here we are using the variable reluctance type sensor to measure the speed of the rotation of an element, and that information is converted in the what is that electrical signal format. This information is going to be amplified by the signal conditioning block in order to drive the information to the next level. So here the microcontroller is going to be receives the information coming from the instrumentation amplifier. So here actually the information coming from the signal conditioning block, that is nothing but the instrumentation amplifier, is in the analog form, but we are supposed to convert that one into the digital form, because in order to process the analog information by the microcontroller, that should be converted into the binary combination, which is nothing but the digital signal. But here we are not showing the parallel signal, which means we are going to use the microcontroller which is having the integrated analog to digital converter. So for example, I may go with the PIC 16C71 family. So in the 71, in the PIC 16C71, we are having the analog to digital converter. So I'm going to make use of that particular analog to digital converter to convert the analog information coming from the signal conditioning block. So after receiving the information, you are going to process that information, and if you want to display that information, you are going to send that information coming from the processed by the microcontroller onto the display from the microcontroller to the display. You may use any display over here. Means you may use the LCD display, or you may use the 7 segment display to show the speed of the that particular element. So one of the application of the RPM meter is nowadays we are having the what is that digital speedometers, which are installed in the bikes. So in the bikes nowadays the bikes are having the digital meters. So there we are using one of the application like means the RPM meter application we are using in that particular what is that the vehicle, the two-wheelers or the four-wheelers. Nowadays we are having the digital meters. So previously we used to have the analog meter, but right now they are going with the digital meters. So they are simply using the 7 segment displays on the what is that they install the 7 segment display displays on two-wheeler vehicles. So you would have observed that one here or somewhere. So that's what the main intention is. This is one of the application of the RPM meter. Now let us go for how exactly RPM meter is working. So how exactly the RPM meter is working. So for that we are having the diagram like this. Look at this one. So this entire thing, this magnet, this is a magnet, and this magnet and this rotor with the teeth is acting commonly acting as a sensor to translate the angular speed information into the electrical signal format. We are using the variable reluctance type sensor. So this particular this particular teeth rotor along with this particular magnet, which is wounded with a coil, is forming combined. These two elements combined forming the what is it, variable reluctance type sensor. Variable reluctance type sensor. So here the teeth are there now. So if you see this one, the rotor is getting rotated, but this one on the diagram it is not shown properly. But whatever the teeth we are having, these teeth are uniformly spreaded on the on the surface of the rotor. On the surface of the rotor, they are the equally spaced teeth, and I'm assuming that the number of teeth around this particular surface is going to be the 20 teeth, and they are equally spaced. They are equally spaced on the surface of the rotor. Okay. So if you see this one, I think we have seen this explanation during the what is the stepper motors case. We have seen the reluctance type stepper motor. So there we are having the rotor and the stator with the teeth one. They are the teeth. They are not the magnet. They are the teeth. Okay. So when this particular rotor, which is having the teeth is getting rotated, then then there is a relation between this particular magnet and the rotor teeth. So there is a gap between the rotor teeth, between the teeth installed on the rotor, and so as there is a gap between these teeth, among the teeth which are installed on the rotor surface. So as there is a gap, when the rotor is getting rotated, at that time there is a magnetic field, induced EMF is going to be developed in this particular what is that magnet. So there's a magnetic field which is generated, electromagnetic field is generated in this particular coil, which is acting as a electromagnet. So in this particular coil, there's an induced EMF developed as the teeth are moving, rotating, as the teeth are installed on the rotor is getting rotated, then there's an induced EMF developed inside this particular electromagnetic coil, and this particular information means electromagnetic field means at the terminals of the electromagnetic at the terminals of the electromagnetic element we are having the induced EMF. Now that induced EMF is driven as an input to the signal conditioning block. This particular signal conditioning block is going to be converts our information, the information coming from the what is that from the electromagnet, this information is going to be converted into the pulse format. This information is going to be converted into the pulse format. These pulses are feeded as an input to the 89C2051, which is a microcontroller. So these pulses are fed as an input to the microcontroller. So inside the microcontroller, we are using the timer 0. We know that inside the microcontroller we are having the two timers in case of the 8051, timer 0, timer 1. So we can use those timers as a what is a time delay generator as well as the counters. So in this case, I'm using the timer 0 to count the number of pulses coming through this particular line. Number of pulses coming through this particular line, and these pulses are counted by the timer 0 as a counter. Now the question comes that how long we are going to count these pulses is a question. So here, in order to show the speed of this particular rotor with how much speed it is rotating, in order to show this particular rotor speed, what we are supposed to do means we are not only supposed to calculate the pulses coming from the signal conditioning block to the microcontroller, but we should take some time duration. So we should take some time duration. As we know that we are having the timer 0, timer 1 now. So in the previous diagram, I used the timer 0 as a counter to count the number of pulses coming from the signal conditioning block. But in this case, what I'm going to do is I'm going to use the timer 1 as a time delay generator. I'm going to use the timer 1 as a time delay generator. So when I'm using the timer 1 as a time delay generator, so I'm going to turn on, means I'm going to generate one active high pulse, which you are seeing on the screen, right? I'm going to generate one active high pulse from here to from here to this way. Okay, now. So this is the active high pulse. So during this particular active high pulse, let us suppose I'm generating one active high pulse which whose duration is a t seconds. So how many number of pulses which are counted during this particular high pulse duration? That is going to indicate means number of pulses which are counted by the timer 0 through this particular line during the t seconds. So that is going to shows your what is that speed of the rotor. That is going to be shows your the speed of the rotor. Okay, so that is a main application means the working operation which is there inside the speed measurement is when the rotor is getting rotated, which is having the teeth installed equally spaced teeth on the surface of the rotor. So when this particular rotor is moving near to this particular electromagnetic coil, so it is a coil, right? When it is keep on moving, so as there is a air gap between the teeth, so this air gap takes the responsibility to generate the electromagnetic field within this particular coil, means induced EMF is going to be developed within this particular coil, and that induced EMF is going to be driven as an input to the signal conditioning block. Signal conditioning block will convert this particular induced EMF into the pulse format, and these pulses are going to be counted by the counter. So how long it is going to be count means it is going to be counts the pulses coming through this particular one for a minimum of t seconds duration. Minimum of t seconds duration. Within this particular t seconds duration, how many number of pulses are counted by the counter, timer 0 as a counter. So that is going to be the speed of your rotor. That is going to be the speed of your rotor. So this is a simple way of working functionality of the what is that variable reluctance type speedometer. Variable reluctance type speedometer. Okay. So if you want more information, let us go back to our textbook. So I'm using this screen recording just because of the things which are there in the textbook. Means what I mean to say that the diagrams which are there in the textbook, when I'm going for recording the information, means video classes, at that time they are not appearing properly on the screen. So that's why I'm going with this particular screen recording. So here the same thing. The information is coming from the this particular rotor. So if you see this one rotor, so induced EMF is developed within this coil. That information is given as an input to the signal conditioner. From there to the microcontroller. From there to the microcontroller. Now, so in this diagram, what we are doing is we are using the 7 segment display as a displaying element. 7 segment display as a displaying element. I think we are having a screen. So in the screen, yeah, 7 segment displays are not there. So yeah, over here we are having the 7 segment display. So depending on the speed, what is it, your rotor speed, the information is going to be displayed on this particular screen. Okay, so this is a brief explanation of our what is that angular speed measurement, means RPM meter, which is used for measuring the speed of a particular element. So one of the application means you can make use of this particular RPM meter to measure the speed of your vehicle by inserting this particular setup on the what is that, where we are supposed to use means we are supposed to install this one on the front or rear side of the wheel, or the whatever the vehicle we are using. If you want to know the speed of that vehicle, we are supposed to use the front, or means we are supposed to install this particular RPM meter either at the front wheel or at the back wheel, that is the rear wheel. Okay. Yes, coming back to the display. So here we are using the what is that, 7 segment display. But we know that when you are in what is that, interfacing your 7 segment display to the microcontroller, that should be done via the BC root 7 segment to decoder, which is nothing but the CD4511. CD4511. Based on that only we are having the information over here. Okay, now we are having the information which is trying to show the your information in terms of 4 nines, means 4 7 segment displays are used over here. 4 nines are going to be displayed. Maximum is going to be the 4 nines. Maximum number is going to be the 4 nines. Okay. So another thing is, whatever the microcontroller which we are using over here, it is a 20-pin microcontroller. We list bother about the number of pins available on the microcontroller instead of the 896 whatever the 2051 you are having. Instead of that, if you want, you can go with the 8051 directly. So no need to worry about this particular IC number. Okay, if you want, you can write the 8051. No one will what is that, ask you. So it means no problem at all. Here, whatever the ports and the timers we are having, the same thing is there in the 8051. So instead of using this particular IC number, if you are unable to remember that one, you can use the 8051. But if you are using this particular IC, then definitely the IC size is going to be the 20-pin IC. So don't bother about the size of the thing. Okay. Another case is when you are going for this particular calculation, there are some certain problems which are going to be appear when you are going to make use of this particular setup as a speed measuring element. The thing is, when you are having the teeth to the wheel, that is a rotor which is getting rotated, so there might be a noise which is going to be generated, means which is going to be there might be a noise in linking the signal, that is in generating the induced EMF within this coil. There might be a noise. So that noise sometimes means some of the noise is going to be treated as a high pulse, and it is going to be given as an input to this particular microcontroller. So that is one of the drawback in using this particular what is it, rotating speedometer, means whatever the variable reluctance type sensor which we are using for calculating the rotation of the rotor. So the problem is some of the noise signal may be included. We can rectify that one by properly installing, means the distance between these two should be maintained properly. Okay, if you are doing like that, then this particular setup is going to use the proper signals. Okay, so the thing is, let us go back to our textbook. So here, when you are going for explanation, you are supposed to explain this entire part and also this part and this particular frequency. And the next coming log is going to be the 66, I think so. Yeah, the 66. Wait a minute, which is a little far. Yeah, over here. So the problem with this number is when you are trying to display the information, there might be a trunking the operation or truncation in the sense, or we are supposed to leave some information, means when you are having the value in terms of the decimal fraction, that fractional value we are supposed to lose for some period of time. So there are do's and don'ts, but don't worry about that one while explaining the concept of what is it variable reluctance type stepper motor, which is acting as the RPM meter. So you can explain up to here, so no need to worry about the rest of the things. You can explain up to over here. Okay, over here. So simple case is how many number of pulses which are counted by the counter in the microcontroller during the time delay t. So that is going to be your speed. So we are having the certain calculations and which we are not showing right over here. Okay, now. So RPM meter is nothing but rotations per minute. Simple cases, RPM meter is nothing but rotations per minute. It is not a new one. It is a rotations per minute. In 1 minute, how many rotations are there? That is going to be shown in terms of the pulses, and those pulses are fed as an input to the counter. So here, in case of the 8051 or in case of this particular microcontroller, timer 0 is used as a counter and the timer 1 is used as a time delay generator. So to generate the active high pulse like this, to generate the active high pulse like this, with means timer 1 is acting as a pulse generator. Within this pulse, we are counting the number of pulses using the timer 0 as a counter, Okay, so this is all about our RPM meter. So the next case is we are having the, yeah, digital thermometer. The digital thermometer means LM35 sensor is used as a digital thermometer. LM35. So the main intention of the LM35 is it is sensing the temperature and converting that temperature information into the electrical signal format. So LM35 is there now. So LM35 is acting as a transducer. LM35 is acting as a transducer. Transducer in the sense temperature sensor, which is converting the temperature into the electrical signal format. So here, for every 1 degree variation in the temperature of the environment, the equivalent value is going to be the 10 millivolts. Means whenever there is a 1 degree centigrade variation, then the output signal is going to be the 10 millivolts. If you are having the 2 degree centigrade at the input of the transducer, output is going to be the 20 millivolts. Means for every 1 degree variation, there is a 10 millivolts rise in the output of the transducer. The voltage is going to be rising by 10 millivolts for every 1 degree centigrade variation at the input of the transducer. Okay, so this is what we are having the LM35. LM35 is a what is that? It is measuring the temperature, and the temperature value is going to be displayed in terms of the voltage, and that is given as an input to the next level. So whatever the LM35 we are having, so let me go to the slides. Whatever the LM35 we are having, that particular LM35 is having the features like this. You can see these features in textbook also. So the features are like this. Okay. So whenever there is a 1 degree variation, for every 1 degree variation, we are having the 10 millivolts of increment at the output of the LM35. Means if you are having the 10 millivolts, then the output is going, 10 degrees centigrade, then the output is going to be the 100 millivolts. So for every 1 degree, it is going to be the 10. So for 10 degrees centigrade, it is going to be the 100 millivolts. If you are having the 35 degrees centigrade, then the output is going to be the 350 millivolts, like that. For every 1 degree variation, it is going to be converts the that temperature value into the equivalent voltage form. equivalent voltage format. So using the LM35 transducer can be used for sensing the temperatures from minus 55 degrees centigrade to 150 degrees centigrade. Minus 55 degrees centigrade to 150 degrees centigrade. Beyond this means you can't use the sensor to measure the values less than the minus 55. You can't use the LM35 to measure the temperature which is greater than the 150 degrees centigrade. Even though these are the practical values, better to use the transducer within this limit. Means you may go for minus 50 to minus 50 to 145, so that it is going to be the safest one, even though it is showing the value like this. Okay. So another case is the operating voltage is going to be the 4 to 30 volts, but in general we are going to give the 5 volts of power supply to enable this particular LM35. Yeah, over here we are having this one, right? LM35 is used to, and I'm using the 5 volts as a 5 volts as a power supply to this particular one. So it is the LM35 is a 3-pin IC. So 3-pin IC na wait. So this is a 1 pin, this is a 1 pin, and this is a 5 volts pin, and this is going to be the output pin. So 3 pins are there. Out of 3 pins, actually this transducer is there in our lab, but unfortunately as we don't have the chance to see those things, we can't do anything. But LM35 is there. I am having that particular LM35 transducer. So there are 3 pins. One pin is should be connected to the plus powers, another pin should be connected to the ground, and the middle pin is going to be act as a output pin. So middle pin is going to be act as a output pin. Here, as we are having the transducer over here, and this is a transducer na. In general, measuring system is contains what ma? Transducer following by the amplifier. Transducer following by the amplifier. So here I am using the amplifier to bring the output voltage of this particular LM35 to a certain level, so that it is going to be sensed by the next level devices. Okay, now so if you want to see that one, let me go back to the diagram. Yeah, textbook. So here, over here, we are having the what is that? The diagram, the same diagram which we have seen, but I think it is not there. The next coming diagram is not there. Yeah, if you see this one, in this diagram, we are having the output of this one. The output of this one is going to be connected to the microcontroller, just like this one. So here we are having the signal conditioner now, which is nothing but the amplifier. So same setup is right over here, and I'm going to use the microcontroller as a what is that microcontroller. So in this microcontroller case, here the information coming from the transducer is in the analog form because it is in the voltage form. So this information is going to be converted into the digital format with the help of the analog to digital converter. The center setup is there in our lab. I'm having my own what is that 8051 trainer kit. So on that trainer kit, we are having the LM35 along with the what we say that analog to digital converter to convert the information into the digital format. And from the analog to digital converter, we are going to give that information to the microcontroller. But here you may use, in this case, you may use the 8051 or you may use the 16C71 family. If you are using the 8051, you are supposed to use the external A to D converter to convert the analog information into the digital format, and that information is going to be given as an input to the microcontroller, which is nothing but the 8051. Okay. Otherwise, if you are using the PIC16C71 family, PIC16C71, at that time, inside the 71 family, we are having the analog to digital converter. Now, this one is going to be directly connected to the analog to digital channel. One of the analog to digital converter channel, which is there in the 16C71 family. So that is internally it is going to be converts the information into the 8-bit format. 8-bit format in the sense, yeah, analog to digital converters which are there in the 16C71 are the 8-bit analog to digital converter. So the analog information is converted into the equivalent 8-bit format. But with the help of the 8-bit, how many combinations we are going to get? It is going to be the 256 combination. The number is varying from the 0 to 255. The number is varying from the 0 to 255. Number is varying from the 0 to 255. Okay, wait a minute. 0 to 255. Okay, now using the 8-bit combination, you can get the 256 combination, which is varying from the 0 to 255. But what he is trying to do is he would like to measure the temperature between the 0 to 100 degrees centigrade. So here, as per this setup, you would like to measure the temperature from 0 to 100 degrees with accuracy of 0.5. So further, what he is doing is, instead of means when you are going for the 8-bit 8-bit A to D converter, which is there inside the 16C71 family, So we can't nullify one bit because 7 bits are more than enough to indicate the limit from 0 to 100. 0 to 100 means it is going to be falls under the what is that 7 bit range. 7 bit range. So 2 power 7 means it is going to be the 128 combinations. It is going to be the 128 combinations. So, but it is not possible to convert the 8 bit into the 7 bit. It is not possible inside the 8 what is that 16671 because it is a fixed 8 bit A to D converter. So that's why what they have done is in order to instead of avoiding one extra bit, they are going to make use of the all 8 bits to represent the number. They are going to make use of the all 8 bits to represent the number. They are treating the least significant bit as a decimal fraction, which is indicating the 0.5 degrees centigrade, which is indicating the 0.5 degree centigrade, and remaining 7 bits are indicating the integer value. Remaining 7 bits are indicating the integer value. With this setup, what they are trying to do means instead of going for 0 to 100 degrees centigrade, they have gone for indicating the value from 0 degrees centigrade to 127.5 degrees centigrade. So means instead of what is that avoiding the most significant bit by including the most significant bit, we are having the 8 bits in the A to D converter now. So in those 8 bits, LSB is treated as a decimal fraction, and remaining 7 bits to the left side of the LSB are treated as an integer representation. Based on that, the value which is going to be shown by this particular microcontroller setup to sense the temperature is varying from the 0 to 0.0 to 127.5 degrees centigrade, and we are having the binary combination and the equivalent what is that decimal combination. So we are having the binary combination equivalent to decimal combination. So that is going to be displayed on the screen. Here also you may use means at the output of this one. I think I'm having the interfacing diagram for this. Let me check whether I'm having or not. It is there in the textbook. I think it should be there. Wait a minute. Yeah. So here we are not having that diagram. That is interfacing diagram. But the thing is, if you want to know the complete interfacing diagram, what you do is the output over here can be connected the input over here. So instead of using the what is that 8051 microcontroller, we can use the PIC 16671. I think the last coming over here. Yeah, whatever the output we are having from the instrumentation amplifier, that is a op amp in the last diagram. So that output can be connected over here as an input to this particular pin number 17. Okay, you can connect over here, which is acting as a unlock to digital converter channel, one of the unlock to digital converter channel available in the 7-1 family. And the output of this one can be connected to the what is that the 7 segment display. We can use this 4 7 segment display now to display the information. There is a 127 means one on the 1 7 segment display, two on the another 7 segment display, 7 on the another 7 segment display, and the last one is going to be shows the dot. Along with that, we are going to display the 5 127.5 degrees. Okay, 125 degrees centigrade. Okay, uh, wait a minute. Yeah, done with this. The next one is going to be the yeah. Here, I think we are having the diagram, but I don't have the diagram over here. Is specifically mentioning which channel we are going to use RA1 to RA2 from the LCD. I think LCD. Yeah, I'm having the diagram with me, so I don't have the full length textbook with me, but you can make use. So whatever the structure you can I explain. Yeah, here he is using yes over here. That it is not there, but it is there over here. So the output of that particular instrumentation amplifier is that is the instrumentation amplifier is nothing but here we are using the op-amp. Yeah, the pages are fluctuated. They are not in the order. After 11.10, I think page number 64 in a PDF, page number 64. You should jump back to page number 64, 13.2 is right? 13.10, we are missing one more page. Yeah, it is a flow chart. So no need to worry about this one. No one will ask the programming part. But I am having the entire setup as an application. You can see right now. You can skip out the what is that? This flow chart as well as which is there in the page number 63 as well as this program. No one will ask the program. They'll ask only the thermometer and 64, 64, 61, 63, I think so. We are supposed to skip off the 62, 63, 64. After 64 in digital thermometer, after 64 you should go back to the 63, but nothing to take from the 63 except this table, the continuation to the table what we have seen. So yeah, this is a table. So this table is showing the number now. I just explained. So continuation to this one is going to be the your PDF 63, page number 63. So up to here, no need to take this flow chart and this program. If you want the programming part, we'll see later. Let us finish up the theory part first. But in the exam, no one will ask the programming part. After 64, 63, skip off the 62 for the digital thermometer. Go to the 61 page number. So you are having the what is that op amp output now in the LM35 case. In the 64th page, you have seen this diagram. What is that diagram? Uh, shuffles. Yeah, this diagram. So this output, whatever the output we are having over here, this output directly connected to this input. So that the output of the what I said, we are having the transducer signal conditioner and the output of the signal conditioner, which is nothing but the op amp, should be converted into the what is that analog information is there at the output of the op amp, that should be converted into the digital format now. For this they are using this particular setup. They are using this particular setup, means using the analog to digital converter channel, we are converting the analog information into the digital format. So you may use the 7 segment display or you may use the LCD, but in this case he is using the LCD. But if you want your own diagram and remember the only one diagram, then you can go with the what is that 7 segment display what we have taken for the pay meter. Same diagram you can use over here. Okay, no problem at all. In the display case, you may use the LCD or you may use the 7 segment display. You may use the LCD or you may use the 7 segment display. Okay, so this is all about our what is that digital thermometer. The next concept is going to be the strain gauge. Next concept is going to be the strain gauge. So strain gauge is the one which is means in your textbook you are having the application name as a load cell to sense the strain experienced by a particular cantilever beam. In the strain gauge setup, I think you would have studied that particular strain gauge setup in the instrumentation case. Here are somewhere during the first or second what is that unit? In your second unit, I think. Wait a minute. Let me go back to your syllabus because I don't know what is there in the second unit in your instrumentation. The transducer concept is done. So, transducer concept. Yeah, you're having the strain gauge. You're having the strain gauge, right? Strain gauge main intention is to sense the strain experienced by that particular one of the cantilever beam which is there in the strain gauge. Cantilever beam is used as a measuring element to experience the stress the strain which is going to be placed on that particular cantilever beam. And whenever you are using one of the bar as a cantilever beam to sense the what is that stress, what you are supposed to do means you are supposed to concentrate on the characteristics of that particular cantilever beam. Most of the cases we are going to measure the variations in the variations in that resistance. Sima, the resistance, you know that the basic formula of the resistance is directly proportional to the length of the whatever the element you are taking. Let us suppose I am taking the cantilever beam. If you want to know the means that cantilever beam is having the some resistance now, cantilever beam is having certain resistance, right? So that particular cantilever beam resistance is directly proportional to its length as well as inversely proportional to the area of cross section. In either of case means either concentrating on the length or concentrating on the area of cross section of a particular element, you can easily know that how much variation is there in the resistance of that particular element, in the resistance of that particular element. So here you would have studied the strain gauge. Yeah, you have studied the strain gauge in the second unit. Same thing is going to be applicable over here, but here what we are doing is we are using the load cell. So this one is acting as a what is that cantilever beam. This one is acting as a cantilever beam. Actually, we are having one practical case in the E&I. We have not done that one. They comes under the analog experiments. We done only the digital. So in that analog experiment, we are having the strain gauge. So there we are going to measure the strains. One of the application of the strain gauge, I think all of us seen that one, which is a measuring instrument. Measuring instrument, weighing instrument. You are going to what is that? Grocery shop to purchase the vegetables, right? So there you are using the weighing machine. So that weighing machine is one of the application for the strain gauge. Nowadays we are having the digital weighing machines. So when you are placing your vegetables on the particular one, then it is going to be experiences some stress. So that stress is converted into the weight format, and finally it is going to be displayed on the 7 segment display, so that you are able to read that one in the 7 segment display format, which is there in the red color. Most of the cases we are using the red color, but here are somewhere we are having the green color 7 segment displays in the shops. Okay, so you would have observed that the same application is going to be used over here. So here this one is acting as a what is that, cantilever beam. This one is acting as a cantilever beam, and as I said, if you want to know the stress or the strain which is experienced by the one element, you are supposed to concentrate on some of the characteristics of the element. Means whenever the stress is experienced by one element, if you want to know which characteristics are varying, you are supposed to focus on the certain parameters of that particular element. For example, if you are trying to lift 60 kilometers weight by yourself, so which characteristics are going to be shows your strain experienced by yourself is your face expression. Is it or not? If you are lifting the 2 kg, it is not going to be affected that much. But if you are lifting the what is that, 30, more than 30 kgs, then obviously your face readings are going to be changes. So if someone wants to measure how much weight you are experiencing without knowing that particular weight, explicitly, if they want to know, then simply observe your face expressions, right? So just like that, here also we are going with cantilever beam. So in the cantilever beam, we are concentrating on the one of the characteristics of the cantilever beam, which is nothing but the length or the diameter. You can use area of cross section. You may use the length or area of cross section, because the resistance is directly proportional to the length as well as inversely proportional to the area of cross section. But in our application, we are going to calculate the length. We are going to calculate the length. So that is going to be calculated in terms of the gauge factor. We are having one formula called as a gauge factor. So they are calculating the gauge factor. Load cell, right? Wait. Yeah, they are calculating the gauge factor. Let me highlight this. This is a gauge factor. So it is a unitless gauge factor. How exactly it is measuring and converting. So this is a resistance is changing. Means it is a ratio between the resistance of the element cantilever beam along with the change in the length of that particular cantilever beam. So we are not concentrating on complete length. If you see, you can see the same diagram what you have seen in the what is that, PPT. So this is the diagram over here. Okay, so here we are using the 4 strips. We are placing the 4 strips which are going to be act as a what is that, stress sensors on the cantilever beam. We are using the 4 strips. Those strips are used for measuring how exactly when you are adding the weight over here. When you are adding the weight over here, how exactly the this particular cantilever beam length is changing. So whenever there is a change in the length of this particular cantilever beam, obviously there is a change in the resistance of that one. It means in proportional to this weight, there is a variation in the length. In proportional to this length, there is a variation in the resistance of the cantilever beam. Remember, we are not going to concentrate on the entire length of the cantilever beam. We are going to concentrate only a part of your cantilever beam. Just like our scenario, when you are trying to lift the 20 or 25 kg weight, we are not going to concentrate on the entire body. We are simply focusing on the face expression. The face expressions are more than enough. How much weight is experiencing? We can't see the numerical value, but we can approximate the how much weight could be there based on your personality. Okay, so that purely depends on. It is one of the example. Don't take in another way. So here we are having the cantilever beam, right? So instead of concentrating on the entire length, we are installing what is that, step sensor strips. We are using the strips four strips are there, they are going to be measured the variations in the length in proportional to that resistance is going to be varied. And this entire four strips are there now. These four strips are going to be used as a four elements in the Wheatstone bridge case. Means we are using the bridge circuit. In the bridge circuit, we are having the four arms now. Those four arms are nothing but these four strips status. So whenever there is a balanced condition means whenever we are not applying any weight, then we are setting up this particular entire setup into the balancing condition. So when there is a balancing condition, obviously this particular microcontroller reads what is that the reading as a zero. We are going to know adjust that one to balance this particular bridge. Means when there is no weight, so bridge is balanced. We are adjusting the parameters over here in such a way that the output of this one is going to be the zero. Okay. So that microcontroller displays the information as a zero. Whenever we are applying the weight over here, obviously there is a change in the length of the what is that strain, that is the cantilever beam. So whenever there is a change in the cantilever beam, obviously this balance is going to be the unbalanced bridge. This bridge is going to be the unbalanced bridge, and this information is going to be fed as a analog information to the input of the max triple one. See here, max triple one is nothing but it is a serial analog to digital converter. It is a serial analog to digital converter. Serial analog to digital converter means it is converting the analog information into the digital format. Up to now we have seen only the parallel outputs. Up to now we have seen only the parallel output. Means output of the analog to digital converter is there in the parallel format. Let me show you that one. Output of that one is in the parallel format. Parallel format which was there in the, yeah, we go back to the previous paragraphs. Let us somewhere no, in analog to digital converter case, we have seen the ADC and DSC, na? Right? Page number, I don't remember that. Yeah, over here we are having this. Right. Yeah. So this one, we are having the parallel conversion. This is the analog to digital converter, which is converting the serial information into the parallel format. But whatever the max to triple one we are having, it is going to be the max triple one is the wait. Max triple one is the serial converter. It is not the parallel. It is a serial converter. Yeah, over here it is a serial converter. If you want, you can see this one. This data out, data in. Serially, it is receiving the information. Serially, it is sending the information, and we're having the chip select signal, busy signal, and the serial clock signal. So, with how much speed it is going to be transfers the information. So here the microcontroller is going to receive the information in serial format, not in the parallel format. It is in the serial format, not in the parallel format. So this is the entire setup for the load. What is that? Strain gauge. So we are using the load cell as a strain gauge to sense the strain experienced by a cantilever beam, and display that particular information. We are using this entire setup. So the microcontroller is going to be have certain output display device. So display device may be the, again we may use the 7 segment display or the LCD display. That purely depends on your interest. If you are visa what the user is a little bit far away from your instrument, then obviously we are going with the 7 segment display. If it is very near, then we are going with the LCD display. We have seen the do's and don'ts during the 7 segment and LCD displays explanation. Okay, so this is all about your load cell. The next concept as per our syllabus is going to be, yeah, till now we covered what? We covered RPM meter, digital sorry, rotations per minute meter, which senses the speed of an element. So there we are using the variable reluctance type sensor. So there we are using the tooth means the teethed rotor. So the teeth are equally spaced, and near to that one we are having one coil along with the magnet. So we are having one coil. It is going to be induces the magnetic field into that particular coil, and induced EMF is transferred to the next level, and so on. So that is what the RPM meter, and we are having the digital thermometer to sense the temperature, and after that we are having the strain gauge. After that we are having the strain gauge. Next case is a LVDT. Next case is a LVDT. How many minutes are there? 44. Okay. LVDT, linear variable differential transducer. If possible, I'll cover that one in the next class. So it is a 45 minutes of class. Okay, we'll terminate this one over here. We'll terminate. So let me go back to this. Yeah, let me give a brief overview again one more time about the RPM meter and the digital thermometer and strain gauge. So in case of the RPM meter, as I said, RPM meter is used for measuring the speed of the element, speed of any element. Means we may use the speed. It has a speedometer. So the simple case is we are using the variable reluctance type stepper mode, variable reluctance type sensor to sense the speed of an element, moving element, and after that we are having the signal conditioning block, and after that we are having the microcontroller and output display system. So as I said, we are having the magnet, or along with the magnet we are having the coil. Whenever this particular teeth, where what is that rotor is getting rotated, so at that time there is a induced EMF developed inside this particular coil. That EMF, there is a voltage, a small amount of voltage that is given as an input to the signal conditioning block, and the output of that one is given as an input to the what is it, microcontroller, which is going to be counts the number of pulses coming. Signal conditioner is converting this information, the information, pulse information. See, my induced EMF is going to be developed whenever the teeth is coming near to this particular magnet. Whenever the teeth is coming to near to this particular magnet, at that time a high pulse is generated. When the gap between the teeth is coming across this one, then there is no induced EMF within this particular coil. So at that time, output is going to be the active low pulse. So active high pulse means whenever the teeth is coming to this particular, near to this particular, what is that? Let me take this one. Let me take this. Instead of that, I will go with this. Whenever the teeth is coming to nearer to the this particular magnet, so we are having the one magnet, and over that particular one we are having a coil. So whenever the teeth is coming near to this particular magnet, there is a induced EMF developed within this particular coil. That information is given. Whenever the gap between the teeth is coming across this particular magnet, at that time the active low pulse is going to be generated. Means the EMF induced in this one is going to be the zero. So that is going to be shown as a active low pulse. So that is the scenario over here. Okay. Now, so this is about what the RPM meter, rotations per minute. And the next case is a digital thermometer. Thermometer LM35 we are using. LM35 we are using. If you want to know some more points about this one, we have seen this. One timer is acting as a counter, another timer is acting as a time delay generator. How many number of pulses are counted within this particular duration? That is going to be your speed. Okay, that is going to be your speed. They are going to calculate based on this particular one. Means they will use the timer one as a active high pulse generator. Within that particular active high duration, how many number of pulses are counted by the timer zero as a counter? That is what your speed. Okay, now the next case is the digital thermometer. In the digital thermometer case, yeah, I'm having over here. Yeah, digital thermometer. So in this case, LM35 is used as a measuring your transducer, which is measuring the temperature varying from -55 to 150 degrees Celsius. Okay, so we are going to have the what is that instrumentation amplifier over here. If you are going through the textbook, they have gone for explaining the how this particular what is that gain is adjusted so that it is going to be transferred to the next level, so that it is going to be transferred to the next level. So no need to worry about that information. So after what is that, as we are having the 16C71 family, in the 16C71 we are having the 8-bit analog to digital converter. So but our maximum range is -55 to 120, sorry, 150 150 degrees Celsius in our LM35 case. If you want to measure that one up to the in this explanation they took the 100 degrees Celsius, but more than that when you are using, as you are using the analog to digital converter, they would like to show the information from 0 to 127.5 degrees Celsius. We have seen all those things. So this is what the numerical values, that is a integer as well as a float value, that is a decimal fractional value. The LSB is used as a fractional value and the remaining are included in the integer value. So this is about what element are defined. And the next case is the load cell. Load cell means we are using the strain gauge measurement. So for that, this particular load cell, we are using the four sticks which are measuring sticks which measures the length of this particular cantilever beam over this area. Whenever you are adding the weight over here, if there is a change in the length, then obviously there is a resistance change. That resistance change is going to be brings this particular balanced condition into the unbalanced one. How much value is there in unbalancing? That value is going to be your reading, and this is a serial analog to digital converter, not the parallel analog to digital converter. So this is all about your what is that topics. That is a RPM meter, digital thermometer, and the strain gauge. So if you are having any doubts regarding this one, you can post in the WhatsApp group. While means in preparing the notes also, if you are having any doubts, you can post in the WhatsApp group. The thing is, I'm using the screen recorder just because of the just before the last class. I think in last before the class, I've seen that the video is not recording. The means whatever the whatever the diagrams which I'm showing on the screen, they are not visible properly. So I felt bad. So that's why I'm going with this particular screen recording. Okay. So if you are having any doubts regarding the topic, you can post in the WhatsApp group. Thank you.